And that's it for today. Alright, so let's do chapter 2, linked list. So this chapter is all about basically linked lists. In the chapter, they represent linked list data structures, a thing they define to themselves. In Clojure, linked lists are a fundamental data structure, and so there's no need to sort of define them recursively. Now, there's a big difference between their linked list and Clojure's linked list, and that, their linked list, right, are little nodes that you can modify, right? You can mutate them. While Clojure linked list are are immutable, right? They're like everything else in Clojure; they're immutable, and so certain things aren't possible in the same way. Um, but I think the benefits of mutable linked list are are not worth exploring, honestly. So I'm going to just be doing the problems in uh, Clojure using the fundamental data structures. Furthermore, um, what was I going to say? Yeah. Furthermore, I think it makes. Sorry, I was reading something else. I was talking. I completely forgot what I was saying. All right. Anyway, moving on. So let's open up Emacs, and let's just open the last one we did, which looks like number 9. All right, string rotation, and we'll be moving on to chapter 2. Chapter 2, problem 1, which is called remove dupes. That's CLJ. Okay. Okay. So I'm just gonna copy this guy and oh, you know what? What did I just do? Did I just paste this in here? Let's see. MGS. Alright, well, I don't really know how I did that, but whatever. Okay, so this is a pretty simple one, I think. We can stick with pretty much everything we have here, except it's not going to be called remove dupes. It's going to take a... Alright, sorry. Remove dupes. Write code to remove duplicates from an unsorted linked list. So, important things are it's a linked list and it's unsorted. Alright, so random order, let's say. Follow up. And then there's a follow-up question. How would you solve this problem if a temporary buffer is not allowed? Okay. So, first of all, how do we literally solve this problem? Right? We take a list, and we would... actually, and how would they do it in a language with linked list? I actually don't know what they mean by a temporary buffer. Actually, first of all, let's just check. I feel like there may be a function in Clojure to do this. So let's go to the cheat sheet. Cheat sheet. Yeah. Let's just look at this and see if we see something that's like sequence processing. Seek in, seek out. Get shorter. Here's one. Dedupe. This guy sounds interesting. Return a lazy sequence from consecutive duplicates. Ah, okay. Cool. So we don't even need to write it if we actually can order it, right? And we kind of know we can order it, right? So really, how do you write this? Well, it ain't too hard. You basically write ls, then you say sort, right? Which I think you can sort a list, I believe. That does probably mean creating a local copy of it. And then, so I guess this is what they mean when they say, how would you solve this problem if a temporary buffer is not allowed? Okay. And then if I've sorted it, I can then just actually just use this dedupe thing, which it's not hard to write this yourself, honestly, right? It's but why do that when this exists right here? And so what do we? Well, let's look at what we want. We got our expected, and we got our list, right? And so our expected would be this, and our list might be ls, okay? And so maybe expected on let's say 1, 2, 3. Actually, expected of the empty is the empty, right? Expected of 1 is 1, right? 1. Expected of 1. We might expect a 1 and a 2 from a 1, 1, 2. We might also expect a 1 and a 2 from a 1, 2, 1, right? What else? We don't oh, you know, that's a stupid thing what I just said. This doesn't, I mean, this does work, but, okay. I was jumping. What is wrong with this, right? Well, I mean, I've reordered the list, right? That's the problem. By sorting it, I reordered it. So that's not going to work. This does do... I think that you call that in... It's called dupe in Linux, right? I've used one of these before. Now, what is it called? Unique is what it's called, right? I mean, unique in Linux, right? But yeah, just basically if two things are... That was weird. If two things are repeated or more, it will just unrepeat them. So the cool thing about unique is, right, because the list is ordered, if the list is ordered, unique, can do it in a constant amount of space, right? But what if the list is not ordered? Well, as near as I can think, the only way to do that would be to... if you want to preserve the order of the list... It's true that they didn't really say anything. They just say write code to remove duplicates from an unsorted linked list. I assume they mean we want to keep the order of the list in order. We just want to remove duplicates, right? I assume. So, anyway. So what I was saying is a bit... Let's just do a little sanity check just to see if there's nothing in here that kind of seems like it might help. Random sample... No, we don't need to make it longer. We don't need to do stuff like this. Partition. Now let's think about this. Do any of these help? No, this is about... Okay. What is this? I don't even know what that is. A seek? Huh. Oh, I get it. It's a seek Q, kind of. Right? Is it a pun? Or... I've never used this. I don't know when exactly, but it's not going to help us. Oh, using a seek. Okay, so I don't see anything that immediately makes me think, oh, this will remove duplicates within the list easily. So I'll just do it myself. Alright, so what are we really doing here? Well, we're really reducing, right, the list. And so we're going to take a function, and it's going to take a list itself, and it's going to take a new value that we're trying to put onto the list, right? And, well, that's the ideal. In reality, I think it's going to take a list, right? But it's also going to take a set. It's called, that's weird. Scene, right? We'll call this one scene, right? And what it's going to do is basically, well, let's not worry about what it's going to do for now. Let's just finish out the whole reduction. But what it's going to then take as an argument is the list. Let's just call it the list. No, because then I'm over. Let's call it ls is fine. Okay. And it's going to take ls as the initial list. No, sorry, it's going to take the empty. Just if I put things, will they be in the same? Yes, they will. Yeah. Okay. If I conj onto a vector, yeah. And then we're going to take the scene. Oops, the scene, which is just going to start off as the empty set, right? That's the empty set syntax. Oops. And then finally, we're just going to process the entire list. So the reduce is going to run across the entire list, all the values in the list, and it's going to start with this thing as the first accumulated value, and it's going to run. It's going to basically be building this map every single time. It's the thing it's reducing over, and that's about it. And so v is going to be from ls, right? And so what we need to do is we need to basically ask if if contains scene v, right? If scene, this is kind of a bad name. If v is in scene, right, then we've already processed this item before, which means we don't actually want to use it. And so all we need to do at that point is just return the original map, right? Because we don't need to, we've already processed this thing once, and so let's not add this item, this value, into ls. But if we do have this value, what we need to do is update in m, right? We're going to update, I think actually we're just going to update. We're going to update scene to, we know scene was, oops, I said, actually we're going to update both of them, aren't we? So starting with m, we're going to update scene to contain this new value, right? We're going to conj the value into scene. And we're also going to update ls. We're going to conj the new value. I'm just thinking, sorry. And I think that's about it, really. This is basically just going to run through here, and it's going to build up this whole thing. And then, oh, well, we do need to actually return the list rather than returning the map that contains a list and a scene, right? Because they didn't really ask for that. So the final thing is just return ls, right? So we're going to return this list that we just built. And let's see what we get. Okay. So I was doing like BB, yeah, stuff like that. Okay. Chapter 2, first one. So it kind of looks like it worked, right? And is there anything test-wise we're not thinking of here? Well, how much time do I have today? Okay, so yeah, we need to kind of move it forward faster. Let's just make a weird, crazy case, right? I expect to see 1, 2, 3, 4, but I'm putting in all sorts of crazy stuff. Ultimately I'm putting in 1, 2, 3, 4 as well, but I'm also going to put in a bunch of 1s here and a 1 here as well, but also a 2, 3, 4, and after that 1, and I'm also going to put in a 3, a bunch of 3s in a row, and I'm also going to put in 2 4s. So let's see. Still passes. Okay, well, so I think that's about it, really, right? I mean, that's remove dupes. All right. And let me look. What was I calling? I was saying problem. Oh yeah, I was putting. Okay. Put the name, and then put, yeah, okay, alright. Okay. Kind of a long string, honestly. Maybe we could... Okay. So this is called remove dupes. Oh, you know what? There was a second thing. What if a temporary buffer is not allowed? I forgot about that. Well, I haven't pressed commit yet, so we're too late. But what if a temporary buffer is not allowed? I'm going to assume this qualifies as a temporary buffer. If a temporary buffer is not allowed, like I just don't know what they mean by that. I mean, do they mean I cannot use any additional memory other than just processing? Well, they can't mean that because there's literally no way for me to know when something's duplicated. Do I mean I can only use a constant amount of memory? What if a temporary buffer is not allowed? I don't see how you can identify a duplicate. Okay, I guess the answer is if a temporary buffer is truly not allowed, then I would have to sort the linked list, right? I think it's the best I can do. If I literally cannot use any additional memory beyond just like copying references around or something, I hate limits like that. It just doesn't make even sense. And I usually don't know what you mean when you say that, but I guess you would have to sort the list first, right? And then once it's sorted, you can well, then you can just use like that dedupe function, right? Of course, you destroy your order now, right? I guess the one thing we can do is we can look at the hints. So let's look at the hints. It says look at number 9 and look at number 40. So alrighty. Number 9 is, have you tried a hash table? You should be able to do this in a single pass of the linked list. Well, no shit. Okay. What's number 40? Number 40 is, without extra space, you'll need O of n squared time. Try using 2 pointers, where the second one searches ahead of the first one. So that is actually interesting. Okay. Why would you do that, though? Why would you use 2 pointers at an n squared cost when you could just sort the thing? I have a question. I feel like even still, sorting would be n log n, right? Which would still be better, because I guess then you would effectively have created a temporary buffer. So I guess that doesn't work. Why would you need 2 pointers either? If you're going to do n squared, you might as well just literally... Wait a minute, is that what they said? Let me look at that again. I think I maybe misread it. Number 40. Without extra space, you'll need O n squared time. Try using 2 pointers, where the second one searches ahead of the first one. Why would I even bother doing that? I'm already n squared. Why be clever? Just literally, for each item, ask, does it appear at this point onward? And that's it, right? There's no point in using a 2-pointer solution to that. Just literally do a double for loop. Or whatever, you know? I don't get the reasoning there, honestly. Oh well, anyway, this is the solution, so... yeah, but we gotta put the right number in there. 2.1, okay.